Welcome back. Today we will begin our discussion on friction on an inclined plane. As you can see, we have an object of mass m that is resting on an inclined plane that is inclined at an angle theta to the horizontal. Now, what we have to understand about friction on an inclined plane is that they can give us cases in different forms. Okay, is the body accelerating? Is the body in limiting equilibrium? Is there an applied force? Is the body moving up or down the plane? These are all things that are needed to be understood, and if you do not have a good understanding of the information that is given to you, you will perceive this topic to be very difficult. That is not the case. In our coming videos, we will deal with all the possible cases that you can be asked about friction on an inclined plane. So when we have an object that is resting on a rough inclined plane, this object will have its own weight that is going to act vertically downwards. Okay? And we label that W. There is always a force which is a component of the weight that is going to act parallel to the plane, and it is the force that tends to bring the object down the inclined plane. Okay, that force is always there, and we can call it Fg, right? That force, we can call it Fg. We also have a force known as the normal reaction that always acts perpendicular to the object or to the inclined plane. Okay? That force is known as the normal reaction, and it is represented by the letter R. So what is important to note is we should be able to know the magnitude of Fg. We said that is the force that always tends to bring the object down the plane, and we should also know the normal reaction. Okay, it is the force that is pressing the object on the inclined plane. So our understanding of resolution of forces will help us to resolve these forces, and we will be able to know the magnitude of each of these forces that we are dealing with. So we will start by resolving the weight into a component that is parallel to this inclined plane and into a component that is perpendicular to this inclined plane. We can be able to stretch this R, and let's say we have the line that will come like this. Okay, we are extending the line that will continue with R, and we can also bring a line that is parallel to the plane, and that is how we're going to draw it. Now looking at this, we have an angle here that is 90 degrees. We know that this angle theta here is going to be equal to this angle here. Okay, simple mathematics can give us that. We can prove that to you right now. So if this is the weight of the object that is coming vertically downwards, let me try to extend the line to form a complete triangle. Let's say it comes like this. Here we will have a 90-degree angle. okay? And so we have a 90-degree angle here, and for this theta, let it be any angle. Let's assume that, let's say it is 40 degrees. So you have 90 here, and you have the 40 degrees here, this angle. So 90 plus 40 will give you 130 degrees, right? So what will be this angle here? If this is 40 degrees and you have 90 degrees here, we have to subtract that from 180, right? Because sum of angles in a triangle is 180. So that will be 180 minus 130, and you're going to have 50 degrees. So this angle here is 50 degrees. But if you look at it, the whole of this angle here, okay, is 90 degrees. All right. So if this angle is 50, what will be this angle here? You have to subtract it from 90. So therefore, theta will be 40 degrees. So in short, what I'm trying to explain here is this angle that you have here, whatever it is going to be this angle if you do the resolution. So I hope that point is clear. Now, since we want to resolve this component of the weight into forces that are parallel to the inclined plane and that are perpendicular to the inclined plane, we can call this X and we call this Y. So if we try to extract that triangle out, this is how it is going to look like. We have the weight coming straight downwards. We have Y here, and we have X here, okay? We have the weight, we have the 90-degree here, we have Y, we have X, and we have theta. So we are going to use the trigonometric ratios to be able to tell us the magnitude of X and Y. So we're going to use the SOHCAHTOA, okay? If you are using sine theta, is opposite over hypotenuse. If you are using cos theta, is adjacent over hypotenuse. If you are using tan theta, is opposite over adjacent. So if this is the location of the angle, the opposite is here, the adjacent is here, and the hypotenuse is here. So using sine theta is equal to opposite all over hypotenuse, then sine theta is equal to the opposite is x all over the hypotenuse is w. So which means x is equal to w sine theta, okay? But we know that weight is equal to mg, right? So therefore x will be mg sine theta, okay? And what is this x? The x that we have here, is the component of the weight that is parallel to the plane, okay? So which means it is going to be equal to this force here, Fg, okay? So we can say x is equal to Fg, so therefore Fg is equal to mg sine theta. And we've said that this Fg is the force that tends to bring the object down the plane, okay? It causes the object to slide down the plane. It is mg sine theta. Now, if we use cos theta is equal to adjacent all over hypotenuse. Cos of the angle theta will be equal to the adjacent is going to be y, right? So that is going to be y all over the hypotenuse is w. So when you cross multiply, we will have y is equal to w cos theta. Okay, but we know that weight is equal to mg, so therefore y is equal to mg cos theta. Okay, so this y here, it is the component of the weight that is perpendicular to the inclined plane. Okay, and since you have y here, it will be equal in magnitude to r. Okay, so that is why we can say y is equal to the normal reaction r, so therefore r is equal to mg cos theta. Okay, r is equal to mg cos theta. Now, why is this important? Why do I have to know that Fg, that is the force that tends to bring the object down the plane, is equal to mg sine theta? And why do I have to know that the normal reaction R is equal to mg cos theta? The reason is you will be asked, okay? They can question you on this. They can ask you to find the force that brings the object down the plane. They can ask you the normal reaction. So you should know that the force that brings the object down the plane is mg sine theta. The normal reaction is mg cos theta. We want to talk about a special case that is known as limiting equilibrium. So what is limiting equilibrium? We have discussed that previously. Okay, so we say limiting equilibrium is a condition when the object is about to slide. Okay, so this object that is currently at rest, if it is about to slide down the plane, we're going to have a force, okay, that is going to act in the opposite direction, known as the frictional force. Remember, we've said that friction will always act in the opposite direction to the direction of motion. So if this object is to slide down the plane, friction is going to act in the opposite direction. Now let's try to write that. So if we have friction acting up the plane F, we've said that in a condition of limiting equilibrium, the forces that are acting parallel to the plane, okay, whether it is inclined plane or horizontal plane, must balance each other. So in other words, the force that tends to bring the object down the plane must be equal to the frictional force in a condition known as limiting equilibrium. Under limiting equilibrium, we said that F will be equal to Fg. Okay, but what is Fg? Fg is mg sine theta, so therefore we can also say that the frictional force is mg sine theta under the condition of limiting equilibrium when there is no applied force. Then the frictional force is equal to mg sine theta. Now I want to remind you quickly about one of the laws of friction, which says that the frictional force is directly proportional to the normal reaction. And we've said that if we want to remove the proportionality sign, we have to bring an equal to sign with a constant. And that is, we said F is equal to mu R. So this mu is the constant. It is known as the coefficient of friction. So if we want to find mu, therefore we're going to divide both sides by R. Okay? So therefore mu is equal to F all over R. So what is F? We said it is mg sine theta divided by what is R? It is mg cos theta. So mg will cancel mg. We have mu is equal to sine theta all over cos theta. So mu will be equal to tan theta. Remember, sine theta divided by cos theta will be equal to tan theta. So in a question where they don't give you the coefficient of friction, but you know that the object is in limiting equilibrium, then you can find the coefficient of friction by using tan of the angle, okay? In our next video, we will talk about the details of friction on an inclined plane. The way I want to simplify it is, there are three important questions that you have to ask yourself when dealing with friction on an inclined plane. The first question is the object moving up the plane or down the plane? Is the object moving up or down the inclined plane? Why is this important? Because it will tell you the direction of the frictional force. If the object is moving up, the frictional force is going to act down the plane. If the object is moving down, the frictional force is going to act up the plane. So that is why the direction of motion is very important. Then the next question that you have to ask yourself is the object in limiting equilibrium or in acceleration? Usually the question that they will give you, it has to do with limiting equilibrium or acceleration. And sometimes they will tell you the body is in static equilibrium, okay? But remember that limiting equilibrium is the maximum state of static equilibrium, okay? All right, so to reiterate myself, it is important to differentiate whether the object is in limiting equilibrium or in acceleration, because that will determine the nature of the equation that you have to form, okay? In limiting equilibrium, the opposite forces acting parallel to the inclined plane will be equal. This is why it is important to know if the object is in limiting equilibrium. Okay, so if it is in acceleration, the opposite forces cannot balance each other. Okay, one of the forces must be greater than the others in order to cause motion. Okay, motion will actually take place if there are forces that do not balance each other. So in acceleration, the opposite forces do not balance each other. So there is going to be a net force, okay, that can be obtained by the difference of the forces that you have, which must be equal to mass times acceleration, since Newton's second law states that F is equal to ma. And the last thing we have to know when dealing with friction on an inclined plane is to know whether there is applied force or not. So we have to know the presence or the absence of an applied force. Okay? These three things will help us to establish our own equation. Okay? Thank you very much for watching this video. In our coming videos, we will talk about the different possible situations that we can deal with regarding friction on an inclined plane. See you soon. Please subscribe, like, and share the video.